Hello everyone, this video is aimed at grade 10 classes doing the CAP syllabus. We're looking at vectors and scalars. We need to learn to draw vector diagrams by scale on a system of axes or on a Cartesian plane. I couldn't find any suitable videos for learners that may still be at home, despite the fact that schools have already reopened. So decided to make one myself. The system that we use in South Africa, obviously our Cartesian plane, which looks like that, we use 0 degrees on the north point of the compass. So where my finger is pointing up is our 0 degree axis. I couldn't find any suitable videos that use that system. A lot of you may be confused with the systems that you might use in geography or in EGD, where the system of axes is pointed on its side. So let's have a look at the step-by-step process that you need to use to draw vectors to scale on a system of axes or on a Cartesian plane, and drawing those vectors to scale. This is applicable to any learner who is doing physical sciences in grade 10 to 12 in South Africa.
Right, so first I'm going to talk about drawing vector diagrams to scale. Okay, so when we are asked to draw a vector diagram to scale, the question will always state that it requires you to draw by a scale diagram. So if a question states that that you are required to draw by a scale diagram, you have to use the diagram to get your answer. You cannot use any other method. So if it is a right angle triangle, you can't use your trigonometry and your pythagoras. You must draw an accurate scale diagram, and you must show through measuring your lines that you have a resultant vector. So first of all, we need to first look at an example, and then we're going to use that example to explain what we're talking about. So here's our question that we're going to look at first. We've got two forces acting on an object, one with a magnitude of 40 newtons on a bearing of 270 degrees, and the other has a magnitude of 60 newtons on a bearing of 210 degrees. So there's a bunch of information, and we need to be able to decipher it and understand what it means. So first of all, we need to learn how to draw a set of axes. So what I'm going to do is teach you a technique for drawing a Cartesian plane or a set of axes. So you will be working on blue line paper. It is a little bit easier to work on graph paper, but you won't be provided with graph paper. So what I'm going to suggest that you do to start with, to draw your set of axes, is that you use the blue lines on your paper to help you draw the initial horizontal line. Then if you mark a dot, you can see I've already marked the position there. If you mark a dot on your page and you place your compass over it, sorry, I can't put my head directly over the compass to read it correctly, so I'll pre-mark the dot. You can see I have marked the dot up there, marking the 90 degree position, and along with this dot here I now will have a line that is perfectly perpendicular and can rule a line through like that, and now I have a set of axes which I know the lines are perpendicular. That's very important. You must have two lines that are perpendicular so that the angles between each of the lines is at 90 degrees. Now let's establish a frame of reference on this system of axes. In South Africa, following the CAP syllabus, this line here is your line of 0, sorry, that degree sign should be up there. That is your line of 0 degrees, and then you work clockwise off that line. So this is 90 degrees, 180, and 270. So you may have learnt other systems of drawing axes, for example in geography or in EGD, and you may watch other YouTube videos where people show you how to solve vector problems using other systems of axes. If you are in South Africa and you are following the CAP syllabus, you must use this point as your 0 degrees and work clockwise off that. That establishes your point of reference being that point, and then we all work off that point in the same way, and we'll all get to the same position that way. Then we need to work on a couple of, we need to define a couple of things or understand what a couple of things are. So some terminology. We'll come across component vectors, right? So your component vectors, you can see this question that we're dealing with here. We've got two forces acting on an object. So each of those forces is a component vector. Remember, a vector is a quantity that has both magnitude and direction. So we're giving magnitude and direction for each of these vectors. You can see there is the magnitude and there is the direction. So let's just determine what these component vectors are. So the first one is 40 newtons on a bearing of 270 degrees. Now please understand that when you are drawing a vector scale diagram, that you must draw to scale, okay? And your scale must be consistent, otherwise your diagram is going to be inaccurate, right? So let's start off by drawing a 40 Newton line on a bearing of 270 degrees. So I'm going to choose to use 1 millimeter representing 1 Newton, and because it's on the 270 degree line, I can draw it like that. Hopefully the color will come out over the black line, and that point there is the end of my vector. So now I have one component vector, okay? So I have one force acting on an object. Now there are two methods for drawing vector scale diagrams. I am going to pretend that both forces are acting at the same time and show you the parallelogram method first of all. Now, if we use the parallelogram method, we work off the same set of axes, so I can work off the same point to draw my second line, and that is a 60 Newton line on a bearing of 210 degrees. So I can put my compass on there, measure the, so remember this line is 180 degrees, so if I put a dot on the 30 degree point, and then I'll go through my origin, and draw the second component vector at you have to be very accurate with this, by the way. You have to make sure that your points are discernible. I would recommend that you use a very sharp pencil. The lines that I'm drawing are a little bit too fat, but I'm trying to use colored pens so that I can demonstrate the drawing of the lines for you and so that you can see the difference. So we now have our two component vectors, and they are drawn to scale, and they are both drawn to the same scale, right? So we've got a 40 millimeter line representing a 40 Newton force, and we have a 60 millimeter line representing a 60 Newton force. Now, because we are using the parallelogram method, we need to draw parallel lines. So using my blue lines on my paper, because this line up here is exactly on the axis of the blue line, it's very easy for me to draw a parallel line, and we will draw it at 40 millimeters in length to match the 40 Newton line up here. Now I'm actually demonstrating the head to tail method. So when you're drawing a head to tail method of vector diagrams, what you're doing is you're pretending that you have one force acting, and that force stops acting, and then that your second force acts subsequently. When you're doing a parallelogram method, you are pretending that both forces are acting at the same time, like that, and giving you your resultant. Okay? So you can see here I've got a tail to a head, and then the tail of the next vector to the head of the next vector. Okay? So here we're demonstrating the head to tail method. But for the parallelogram method, I've got these two lines as being parallel. And now, if I draw this line, it will be exactly 60 millimeters. Okay, so you can see it is 60 millimeters. And that gives me the point at which my resultant will end. Okay, so the resultant vectors, when you add together the component vectors, that will give you the point at which your resultant vector must be. So we draw a line from the origin of our axis across to the point where, if you're doing head to tail, okay, to the point where your second arrowhead meets, or if you're doing a parallelogram, the opposite end of the parallelogram, and that will be where your resultant vector, so we'll put it there to label it, that will be your resultant vector, which is if you add your component vectors together, that is what the resultant will be. Now, to determine the value of that vector, we need to first of all measure it. So if we put our ruler on the line, we are getting a total of 86 millimeters. Okay, so we're getting 86 millimeters, and then we put the compass on the diagram, and sorry, I'm going to have to move all of these out of the way. And we've got to make sure that we are accurate with that, and I am getting, that's going to be 200 and, well, the angle I'm getting there is 53 degrees. Okay, so that's this angle here is 53 degrees. But remember that the angle that we're looking at, we always measure off the 0 degree line. So we're looking at this full angle. Okay, so because the angle that we have measured, which is this angle here, is only 53 degrees, we need to add the 180. So to get our theta angle, we've got 53 degrees, add 180 degrees, and we are going to get 233 degrees according to our scale diagram. And that is how you determine the magnitude and direction of your resultant method, of your construction method, when you are doing by scale diagram. Okay, so the question will always state by scale diagram. You have to use your ruler to measure and use your compass to measure the angle. And the model answer for this question gives an answer of, so let's just work out, the 87 millimeters gives us 86 newtons, because we use a scale of 1:1, and our bearing there, we've shown how you calculate your theta angle. It is then very important that you write your concluding statement to give your answer. Okay, so the resultant is 86 newtons on a bearing of 233 degrees. That is your concluding statement, and that is how you should approach a problem like this. Now, the model answer for this question gives an answer of 87 newtons, so we're only 1 newton out there on a bearing of 233 degrees, which we've got perfectly. You do have a small margin for error in problems like this. It depends on the question as to what your margin for error is, but this example, if I had produced something like that, I would get full marks for this, even though we're 1 degree out. That would be well within the margin for error, and that is how you draw vector diagrams to scale. Okay, it's up to you to choose what scale you want to draw, and that is how you use your system of axes off the 0 degree line. The 0 degree line must be the one that points straight up, or the north point of your compass. Okay, so that would be north, that would be south, this is west, and this would be east. So your north line or your 0 degree line is where we work off, and we work in a clockwise direction off that, so that we have a fixed reference point and we all know where to draw from there. Let's now look at working by calculation. Right, so now we are looking at determining a resultant vector by calculation. Okay, so very important, your question will always state determine the resultant vector by calculation. Again, we have the same system of component vectors, okay, and you will be using the parallelogram method in this case to construct a triangle, and then you'll be using that triangle to do calculations off. Now, when you have a question like this, I would suggest that you still draw a fairly accurate sketch of your triangle or parallelogram. So it is still an important tool. It's important to label the sides of a triangle. I'll explain why now. So let's have a look at an example, and we will look at that question there. So we have two forces, so we've got two component vectors. One is 150 newtons on a bearing of 180 degrees, and the other is 85 newtons on a bearing of 90 degrees. Now, because we are doing it by calculation, it's not that important that you draw it to scale, but I would still try. So I'm just going to scribble it out. I'm deliberately not going to measure. So this is our reference point, and we're going to be using the parallelogram method because both vectors are going to be coming off that point. So in our heads, we're thinking that both forces are acting at the same time, and I'm going to draw what I'm going to call and I'm just making it darker so that you can see it. I'm going to call that 150 newtons. And now we have another one of 85 newtons, so we'll make it a bit shorter and try and darken it up so that you can see it. Okay, so I've deliberately drawn it a bit shorter. So we've got our two component vectors there, so we know that our resultant vector is going to be somewhere in this direction. Now we need to kind of draw some parallel lines. Again, we don't have to be too strict, and then our resultant vector is going to be, doesn't even have to be a straight line, but use a ruler. Okay, so our resultant vector is going to look like something like that. Now it's important that we do that for a couple of reasons. One is that you need to label your triangle. So I am going to choose to use, and this is where I've used all the different colors, I'm going to choose to use this triangle that I'm now outlining in blue. Okay, that makes this angle the angle that I'm using, which I'm going to call theta. That is convention that we call it theta. Okay, that makes this line opposite, that makes this line adjacent. Okay, so always label the sides of your chosen triangle and the position of your theta angle. It will help you with your calculation. Now, what we are going to do is, because we always have a right angle triangle, so with these problems that you are determining by calculation, you will always have a right angle triangle. So in this case, our right angle is there. Okay, and we can label that we have this line, let's cross that out. This line is 85 newtons and this line is 150 newtons. Okay, so we now know that our opposite line is 85 and our adjacent line is 150, and we are going to use we're going to use the Pythagoras' theorem to determine the magnitude of the length of the line, and we are going to use trigonometry to determine theta. So first of all, let's look at the magnitude, and we're going to use Pythagoras. Okay, so it doesn't really matter which way around you label in this case, because it's not going to make any difference to your calculation. That will make a difference later. So we've got 150 and we've got 85 as the length of our sides, and that will give us the length of our hypotenuse, which in this case we've called it R, and that will be our calculation, and it will give us a magnitude of 172.41, and that will obviously be newtons, being our unit, and that is the magnitude. Now we are going to calculate bearing using trigonometry. Okay, now if you remember from maths, you should have hopefully learnt that little mnemonic. Okay, SOHCAHTOA. That stands for sine equals opposite over hypotenuse, cos or cosine equals adjacent over hypotenuse, and the tangent or tan equals opposite over adjacent. So SOH, sine opposite and hypotenuse, CAH is cosine adjacent hypotenuse, and tangent opposite over adjacent. Now because we have the value of the opposite and the adjacent, we have to use the tangent. Okay, so tan theta equals opposite over adjacent. The values that we have for the opposite and the adjacent, this is where it's important. Okay, you can't swap these values around and expect your value to come out correctly. Because I'm using this triangle here, the opposite is 85, the adjacent is 85 newtons, and that will give me this angle as theta. So that's 85 over 150. That gives me the theta angle is 29.53 degrees. So this is 29.53. Okay, but then we have to calculate bearing. Now remember that we always operate off this line as being 0 degrees, and we want the angle, we want that angle. So we're not interested in this 29.5 degrees. We want the red angle that I've just drawn in now. So to calculate the bearing, we have to take 180 degrees and we have to subtract theta. Okay, often you guys will get to this point and you'll stop and you'll forget to calculate your bearing, and that will give us our theta angle. So we're going to get an angle of 150.47 degrees. Let's just move that all up. Okay, so our bearing is 150.47 degrees. Don't forget that step. Now, you've completed all your calculations. So you've got your magnitude as being 172.4. Oh, it's off the page. It's 172.41 degrees. 172.41 newtons. And we've got our bearing as being 150.47 degrees. Okay, often you guys will stop there and you will forget to carry on, so you must write your concluding statement to finish off your question. And your concluding statement is that the resultant is 171.41 newtons on a bearing of 150.47 degrees, and that will give you everything that you need to complete and determine a resultant vector by means of calculation. So please, you must remember all of those steps. You must remember that you've got to once you've got your magnitude using your Pythagoras' theorem, you've got to remember that you calculate your theta angle. You then must calculate your bearing once you have your theta angle, and it depends on which quadrant your theta angle is in as to how you're going to calculate that. So if it's in quadrant 1, sometimes you'll just be able to use it straight away. If it's in quadrant 3, you might add it to 180 degrees or subtract from 270, and if it's in quadrant 4, you might subtract it from 360 or add it to 270. So this is the fourth quadrant here. So it just depends on where your theta angle is as to what you're going to do with that. Then you must calculate the bearing of your line off your 0 degree line, and then combine these two answers that you see here and write your concluding statement as a single answer to conclude your question. Okay, so you must remember this final step here and write your concluding statement. And that is how you determine a resultant vector, by means of calculation. Okay guys, so just to summarize that then, when you draw your system of axes, so here I've got some graph paper which does make it a little bit easier. Remember, you must start with an accurate set of axes. These lines must be exactly perpendicular to one another, otherwise it's going to screw everything up. Okay, this is your 0 degree line here. So 0 degree line, if you want to call it your north pointing line, that is where 0 degrees is, and then we work clockwise off that, making that 90 degrees, 180 and 270. Okay, so you really you must have that right, and then you must act off your reference point. Okay, then just a couple of things. If I am doing a head to tail method, and say for example I have a vector, let's just draw it in a clear space. So let's say I have a 60, let's just call that a 60 Newton line, and it's operating off that bearing, which I don't even know what it is. If I'm doing the head to tail method, I then have to draw another set of axes at that point, and because I've got graph paper, I can draw it really quickly because I have all of the lines. So I can draw another system of axes, and that system of axes will be exactly parallel to this one now, and then I can draw my subsequent vector off that point, and I know it will be accurate. So if I'm trying to draw an approximately, let's use the compass this time, and let's say we're trying to draw a line at 45 degrees, that'll be 45 degrees, and we're trying to draw, let's call it a 40 Newton line, so that will give me, if I'm doing head to tail, that will give me the point which my resultant will get us to. So my resultant vector, if I'm doing head to tail, will be there, the red line. Okay, and I can then determine its bearing using my compass, and I can measure it using my scale of 1 to 1, and for that one we'll get 86 newtons on, and that angle there is my theta angle. So that's if you're doing head to tail. Okay, you must draw another set of axes there, and it must be exactly parallel with your original set of axes. If you draw a parallelogram, let's just do the parallelogram. You can see for my second component vector, I can use the same set of axes to draw both that line and that line, and then from there all I have to do is make sure that I've got my lines parallel. And in this case, my parallelogram, you can see that this line is going to be parallel to that line, and we've got our parallelogram set up there now. And now if we had a right angle triangle, which we don't, we could choose our triangle, but it's very important to understand that you need to, if you're doing head to tail, that you need to draw another set of axes at that point. Okay, if you have 3 vectors, and you are doing vector addition, you must use the headers to tail method. Okay, so that is the only time that I would recommend that you are you're forced into using one method or the other. If you only have two component vectors like we have in this question, then you can choose between either when you are doing your method of construction. It's only when you have a resultant vector out of 3 or more component vectors that I would advise that you use the head to tail method and draw the new set of axes every time you have an origin. Okay, so I hope you find that helpful, reviewing all the methods for determining resultant vectors that you will need for grade 10 following the CAP syllabus in physical science in South Africa. Hopefully those of you studying at home can use this, and for those of you revising at the end of the year before the November/December exams this year.